Okay, in this video, we're going to be looking at transformations of exponentials and logarithms. Just going to turn the screen around. Okay, so when we're looking at transformations, I guess we can do a quick talk about exponential graphs, and you'll find that on this page there's some information about it. Okay, so you can scroll through those and listen to some of the words and the dilations and all that. Because what I was going to do is just have a quick look at those graphically. Okay, so if we just go onto a graph here, and what I've got here is really a general exponential graph. Okay, and I don't know if you can see my cursor here, but you can see there's a point where it doesn't go any further. Okay, and this is like an asymptote. So when you're looking at a basic equation of an exponential, generally they first key part and the main key part is the asymptote, which I've just drawn there. You'll see it's got a y-intercept, okay? But also you'll notice that if you actually look at this green shape, it's always increasing, okay? So you could always say the slope of the graph is positive. And also you could say it's always concave up. So you could actually say that the double derivative is also positive. Now, if you change some values here, you can see, if you follow my cursor here, you can see that there's some different values here. If you change the value at the back, which is D, I'm just going to do that now. I hope you can see that all that does is just lift the graph up or down. It doesn't change the concavity. It's always still increasing. The only thing it changes is the asymptote, all right? And in actual fact, the asymptote just becomes whatever that D value is, okay? So in this graph here, the asymptote becomes 1.1. Okay, if you change things like C, so C is just a thing up above there. It doesn't change the asymptote either. All it does is it just moves it left or right. Okay, so I'll just put C back to 0. But if you change things like A, what it does, it doesn't change the asymptote again either. What it does do is make it more skinny or wider. However, if you make A negative, that's the key there, the asymptote is still in the same spot. It changes the slope to be negative, and it changes the concavity as well to be concave down. So I know it's a bit quick overview, but really when you're graphing exponentials, you've got a calculator. I guess the key is spotting the asymptotic behavior, okay? And you can spot that from the number at the back. So if you go to your questions on the next page, I'll just click on that here. So we'll just move on to the next page. It does talk about a few other things. We really don't even need technology to do this one. But if we do a quick sketch of this graph, like I said before, really it's the number at the back there that is actually the value that is going to change it. All right, so I'm just going to find my graphs again. Okay, so if you're looking at this graph, you can see that this value at the back is a +1. So what it really means is the original graph is going to be shifted up by 1. Okay, so the asymptote, which was at y = 0, now becomes at y = 1. You could find it's still going to be like all the others where it's going to have that shape where it's just increasing. Okay, the A value at the front is actually just 1. So it's actually when it's a negative that makes it go down. So if we just want to find the y-intercept, that's the only other key feature really we need. That's when x = 0. Okay, we would have y = 3 to the 0 plus 1. 3 to the 0 is 1, so 1 plus 1 = 2. So we know that when x is 0, y is 2. I'll just put that one on here. And like I said, you can have your graph, your calculator out with you. Here's a quick sketch though on the graph. All right, so moving on to the next question here, it just says, what's the domain and the range? Okay, so I hope I'll just have a quick sketch of the graph in front of us when I do that one as well. So if you've forgotten, domain is basically what x values does it exist for. Range is what y values it exists for. So again, if we're having a quick look at that sketch, we have the asymptote here at y = 1. I hope you guys understand that the x values are going to keep, it's okay for any x value that goes on forever and ever, that to the negative side, that way. And even though it looks like an asymptote, there is no asymptote here. The graph is just going to keep increasing and going up and up. So how do we do domain here? So I guess we just sort of say the domain, and this is one way you can do it, is you can say x belongs. So that sign there is belongs to all the values that exist in real life. Okay. Another way you could do it is you could say x is between positive infinity and negative infinity. A bit hard to read that. But that's how I'd probably write those. And if you're looking at range, range does look a bit more fixed. So range is all the y values. Now, hopefully you guys can see that y cannot go below 1. And in fact, it cannot be 1. It's an asymptote. So the y values are greater than 1. Okay. Then its last question says, describe the transformations to get from your original graph to this one. So just note, the original graph is not just 3dx, it's 3dx plus 1. So I hope you guys understand that the number at the back just talks about how far it moves up. So if you started at +1 and then it went to +4, really, you've just gone up another 3, okay? And this thing here is like left and right movement. At the moment, it hasn't gone left or right at all. So we've actually gone 2 to the right. When you see that thing around x there, it's a bit like, just think about quadratics. Remember, you start with x squared. If you had x take 2 all squared, we're going 2 to the right. It's the same idea, okay? Now we can use fancy words like translating horizontally. So if you could talk about up, you're translating vertically, up by 3. And if you're going to the right, we can talk about translating horizontally, 2 to the right. Any of those is fine. Okay, so moving on, there's some questions from your books as well to do as well here, but moving on, we're supposed to be looking at logarithms in a little more detail. So if we go to the next page here, you'll see that there's an investigation, all right? And it just says that there's some key features of the logarithm to start with. So we'll just talk about those quickly. So hopefully you can see from this graph here that the x-intercept is 1, so it's there, okay? The vertical asymptote, so it's actually sort of the opposite. We have a x equals asymptote. There it is, x equals 0. So for these guys, it's the opposite. We cannot be less than 0, okay? So you must realize that this value here is always positive, okay? It is continuously increasing, okay? And you could also add another one too. You could actually say it's actually concave down if you wanted to. All right. So using those key features, we're supposed to do a bit of an investigation here. And because you really haven't done much of this at all, it might be quite unfamiliar. So we've got these two graphs. They're much better to look at graphically on the left here. It says using the words like dilation. So dilation means multiply, asymptote, x-intercept. Talk about what's changed from both those graphs. So I hope you guys can recognize here that the x-intercept stays the same. All right. The asymptote, there it is, it's still there. The asymptote stays the same. Okay, and we might write that underneath, that's x equals 0. Okay. It's just how do we describe the difference? So the red one's the original, and it might be hard to see, but you can sort of see it here. This, if you look at this value here, it's sort of 1 away from the axes. If you look at the new one on the next graph, it's actually 2, right? We could find another point that will reflect that. Here is one where it's roughly 2 away, and this one's actually 4. So and it actually happens on this side as well, but it's a little harder to see. Whatever that distance is, it's doubled. So what we got is one of these things like multiplication, okay? It's a multiplication of 2. So instead of saying multiplication, we say it's a dilation of 2. So it's a multiplication of 2 from x-axis. And I hope that makes sense there, because it's actually, from the x-axis is where all this multiplication is going from, okay? Moving on to the next one. Imagine that we make a change to the graph by adding a value at the back. And really, that's just like exponentials, okay? I hope you guys would understand that whatever this point was, let's try and pick one. There we go. That was the original x-intercept. Guess what? It moves up by 2. This one goes up by 2. This one goes up by 2. So using such terms as x-intercept, asymptote, explain what's changed. So in this case here, the x-intercept has changed. Okay, I'm not sure what the new value is. There it is over there. Not sure what that is, but we'll leave it. X-intercept has changed. The asymptote is still the same because you're just moving up, aren't you? Asymptote same at x equals 0. All right, but what we have done is, and we use the word translation this time. Translation is what we do when we go up or down, okay? So we got a translation, sorry, I forgot to say it's a vertical, so it's going up. Translation up of 2, okay? So up by 2 is fine. A vertical translation of 2 is fine. That's what's happening in that graph there. Okay, moving on to the next investigation part. It says what happens when we change the value inside of x take 3. And you might not see it straight away, but you'll spot it with the asymptotes. The original asymptote was here at x equals 0. The new one becomes x equals 3. And it's just like I was talking about the exponentials. You need to realize that this is really like moving 3 to the right, okay? See, if you look at the original x asymptote, x-intercept is 1, it now becomes 4, okay? So we can actually say that the x-int moved 3 to the right. The asymptote moved 3 to the right. And really, we can just say graph is horizontally. That's a new word, isn't it? So I'm just using this one this time. So it's a horizontal. Horizontally moved 3 to the right. So you can use the word translation as well. So it says here as well. So maybe we could have said graph is horizontally moved 3 to the right. You could have said instead of move, just translate it. Look, those words are quite big, so you don't have to remember all of them. If you can remember left, right, up, down, that's probably going to be good enough, I think. All right, so that one's pretty clear what's happened. That one's probably the most obvious one. One of the most complex ones is this one here. Okay, and there's difficult ways to describe this one. And I'm going to describe it in one way. Okay. So let's have a look. So the original graph is ln x, and the next one is 2x. So we can actually see it's sort of moved this way. Okay. So we can actually call it, this is, remember before we talked about some movement up and down from the x-axis, you can actually say it's movement from the y-axis. So you can actually use the word dilation, but we generally don't use that one. Another one is a very smart way, and what we can do is use our log laws. In actual fact, that's the actual same as ln x plus ln2, okay? So if you remember on the previous page, if you saw something added at the back, you know, so that's one way to talk about it is like a dilation, but I'm going to scrap that one out. A quicker way to think about it is going, you know what? I've just moved everything up. So we could just say move up ln2, okay? And hopefully you can see that the asymptote, so the asymptote does not change. Okay, it's still at x equals 0. Our x-intercept will change, x-intercept changes. But we can use the word, so if we want to be fancy, we've got a vertical translation of ln2 units up, okay? I'm running out of space, but you could actually say it's a vertical translation of 2 up, all right? So that one's probably the bit more difficult one to see there, okay? And in summary, we can actually talk about what all these things are doing here, okay? So the K, this one at the front, really, it just makes it skinnier or wider. So it just makes the graph steeper. A, that's the one we just talked about before. That's a up or down. Okay. B is left or right. And C is up or down. Okay. So I'm just going to keep them simplified there. When we do the examples on the next page, it will be a bit more complex. So we didn't actually really even mention K. Maybe I'll just go to a graph for you right now. So if we have a look at a graph here, I've got here's y equals ln x. Okay, you're not working. There we go. So here's the graph of y equals ln x. If I graph another graph next to it, which is k ln x, there it is. So I don't know if you can understand what I'm doing here. What I'm actually doing is making the value out the front bigger, right? So if I make it bigger, I'm changing the steepness of the graph. It's becoming much more steeper. If I change the k value to be less than 1, it sort of changes that steepness the other way, okay? So that's what happens with that value at the front. Okay, and we could do all these other values we can change, but I think they're pretty clear from the investigation. Okay, so we'll just go back to the document, and I think we just need to tidy those up. So K does make it steeper. That's what I just showed you before. The A value, that was sort of like moving it up or down by ln units. B, just think about quadratics. Remember, like how had x take 2, it's like left or right. And C makes it up or down. So what we might do is, when we do example questions on the next page, we'll make it a bit more detailed, okay? And that will be in part 2 of this video, okay? So I'll just show those to you. And here are those impacts. So here's the much more technical terms here. So just like I was talking about everything before. So you can see the horizontal movement, left, right, movement up, down. So yeah, there for you to have a quick look at. And we'll look at these examples in part B of the video, okay? And I'll start that and put that on the YouTube as well. Okay, thank you.